Okay, this is how to use Angr and what is Angr and everything about Angr. This is a reverse engineering technology, not an emotion. Yeah, let's get started. So we're gonna be going through like quite a bit of stuff. I think the first five of these bullets are the ones that people would actually care about, and the last two are just like cool things that like research people sometimes do with this. But the first five are like the ones that apply mostly to CTFs. So starting off, we're gonna talk a little bit about compiler theory. Um, so Angr is based off of a lot of compiler theory concepts, and understanding these concepts is key to understanding how Angr works and how you would use it. So the first of these concepts is the concept of a basic block. So this is like a basic block is an assembly sequence of instructions that are that contain no branches except at the end. So it's essentially a sequence of non-control flow instructions followed by like a jump or something like that. So here's an example of like a basic block. It's like some adds, some moves, some random junk, and then a jump. Um, so why do basic blocks exist, right? We can try to decompose our programs into these basic blocks, and instead of trying to understand every instruction individually, we just need to understand each basic block and how they interact with each other. So um, to analyze like a full program, we would decompose our program into a bunch of basic blocks, and then from the last instruction of each basic block, we can tell what like possible successor basic blocks it has. So at the end, there's going to be like a jump equals instruction or something like that. So one possible successor would be the address in the jump, and then the other possible successor would be just continuing without jumping. Um, and we can build like a directed graph out of all of the program's basic blocks, modeling its control flow. So this is an example of what one of these control flow graphs would look like. Um, so this is actually from the 429 bomb lab, I think. I just picked a random thing that I had in my cutter and took a screenshot. Uh, but you can see there's like a jump above and then two addresses or two more basic blocks. And so in the true case, if EAX is above 0x3E8, then we're going to call explode bomb. And in the false case, we're going to run some other instructions. And then the same thing holds for um, the next basic block. So you can see how we can decompose our programs into just a ton of basic blocks, and it makes it fairly easy to see what's going on inside of our program. This is like the good alternative to just looking at assembly. If you're just looking at assembly, like you hate yourself and you're trying to like keep track of uh, which jumps go where, and this just like does it for you. Um, so graphs of this form are called control flow graphs in compiler theory. So they're often just abbreviated to CFGs. And CFGs, if you think about it, they represent every possible path that a program can take during execution. Um, so CFGs are commonly used by compilers to optimize your code, but they're also used by security engineers to analyze programs. Um, so with the compiler theory stuff out of the way, we can start talking about like static analysis using basic blocks and control flow graphs. Um, and how do we actually do anything useful with security using these concepts? So the first thing is like the concept of symbolic execution. So symbolic execution is a static analysis technique where static analysis is just like um, doing analysis on a program without actually running it. So we're not actually going to run the program. We're just going to decompose our program into basic blocks and then do like graph walks on the control flow graph. So the way that we do this is we keep a running system of equations, and each time we exit a basic block, there is generally some conditional at the end of the basic block. It's going to be like compare EAX to EBX, jump like greater than or equal to some instruction. So one condition that you could see would be like EAX greater than or equal to EBX, and that would get appended to our system of equations. Or I guess they would be inequalities. So for an actual example, I think this is the basic block that I took off of the basic block I showed at the beginning of the talk. So we see like some adds, some moves, and then a compare EAX to 0xf, and then a jump not equal to 0x286f. So assuming that we follow the true branch and we jump to the basic block corresponding to 0x286f, we know that it must have been the case that EAX was not equal to 0xf. And if you look through this assembly a bit more, you would notice that that also implies that the memory at RSI plus RAX times 4 is not 0xf. And then for the false case, it's just the negation of these two statements. So we could traverse our graph and do this for every basic block in a specific path through the graph. And that's going to allow us to build some huge system of equations that just essentially describes what conditions need to be true to follow a specific path. So if some system of equations is satisfied, then we know that the path through the program that we're going to take is the one corresponding to that system of equations. So this is like symbolic execution, somewhat simplified, but it's really all that we need to know in order to use Angr. So you might notice that every time we go through a basic block, we split into two new states, right? So we're going to get like an exponential number of states that we need to keep track of as we traverse the control flow graph. And this like exponential blow up makes symbolic execution very slow, and it's one of the like main downsides of symbolic execution. We'll keep this in mind going forward, and I'll talk about it a bit at the end of the talk. But for now, it's not super important. So why do we care about symbolic execution? And the answer is that Angr is essentially based solely on this concept of symbolic execution. There's a few extra things built into it, but at its heart, it's like a Python library used for symbolic execution. So with the symbolic execution out of the way, we can actually talk about what we would use this for in a CTF. So how do we use symbolic execution in a CTF, right? Nobody cares about the theory stuff. Everybody just wants to know, how do I solve a problem with it? So the typical example that you would use Angr for is like a reverse engineering problem that follows the following format. Essentially, the program prompts the user for a password. The program then encodes the password with some secret encoding scheme. we compare the password to the encoded version of the flag, and then if the flag and the user's input don't match, we like output something snarky. So the idea of a problem like this is that you need to reverse engineer the encoding scheme, right? You have to determine what the encoding is going to do, and then try to reverse the encoding on the flag, and then from there, just determine what the flag is. And then if you were to input the flag as the password, it would not output a snarky message, and it would say something like, nice, you got the flag. With Angr, we can cut out the middle step of determining what the encoding scheme actually is. We can just use symbolic execution to tell us right away what the flag is. So this kind of sounds like magic, but I'll talk a bit about how this actually works with pictures. So yeah, normally we would just reverse engineer the encoding scheme. Unfortunately, reverse engineering is hard and a lot of work, and I'm lazy, so I don't want to do that. Yeah, it's also time consuming. And if you're competing in a CTF, you don't want to spend, I don't know, 7 hours reverse engineering something when your CTF is only 2 hours. So going back to our example, let's consider like an actual problem that does what we said it does. It asks the user to enter the flag. It encodes the flag with some really complicated encoding scheme. We compare the user's input with the actual encoded flag. We output nice flag if they got it wrong, or get good if they got it, or nice flag if they got it right, get good if they got it wrong. So if we like simplify the CFG as much as possible, it's going to look something like this, where we do a bunch of garbage to like read in user input, do a bunch of garbage to encode the flag. Then we're going to call mimCompare to compare the flag with the encoded flag, or the user provided flag with the actual encoded flag. We're going to test EAX because mimCompare returns 0 if the flag, or if the two strings match, then mimCompare returns 0. So if we return 0, we're going to jump to the nice flag path. And if we return something that's not 0, we're going to jump to the get good path. So essentially what we want is some walk on the CFG that will end at the good path, right? And any walk on the CFG that ever touches the bad path, we can completely disregard. And notice that once we find a path that gets to the good path, we will have computed a system of equations that need to be satisfied in order for us to get to the good path. So if we can find any input that satisfies that system of equations, then we will have some input that will take us to the nice flag part of the program. And if the problem is correctly written, there will only be one input that does such. So we will have computed the flag. So yeah, we're going to traverse the CFG using an arbitrary graph traversal. Generally, we'll use like a breadth-first search just for simplicity. We're going to throw away any paths that hit the bad path, and we're going to stop when we find any path that hits the good path. Then we just need to find some input that solves the system of constraints outputted by symbolic execution, and this should be the flag. Similar techniques can be used on most reverse engineering problems, actually. Angr supports like most of the widely used architectures. And if you use Angr in a smart way, then you can basically never reverse engineer anything ever again. This also works on self-modifying code. So it's fairly common in reverse engineering tasks to like at runtime patch your own binaries code. So for example, you would have a function that has been encoded in bytes in your assembly file, and as soon as the program starts, it decodes that function into the proper bytes, uh, and then calls that function. So this is a fairly good way to get around people doing static analysis, because the binary is no longer readable assembly. It's just a bunch of garbage until the main function of your binary unzors the assembly and makes it real. So yeah, skipping over the self-modifying part, that's kind of just a neat thing. It's not super important. Notice that we didn't actually do the reversing part of the challenge. We completely skipped over that. We just looked at the CFG, found the two paths that we want to go to and avoid, and then plugged it in and solved the problem. So, okay, I talked a lot about very theoretical attacks, right? How do you do anything? How do I actually implement these attacks? And the answer, we finally get to the point of the talk, which is using Angr. So yeah, okay, symbolic execution, cool. How do I actually use Angr? Angr is essentially just a Python library that provides all of the necessary parts to do useful symbolic execution. So the first part that Angr provides is called symbolic variables. So symbolic variables are the basic building blocks of symbolic executions. This is essentially what gets stored in each symbolic execution state. Most of this is abstracted away from you, so you don't really care about it. However, you might need to know the name of it, so if you're ever reading documentation and they mention symbolic variables, that you know what they are. So if we have some symbolic state as denoted in this box, right? This is our system of equations that we want to be satisfied. All of the things that are not numbers would be considered symbolic variables. So if you think about it, this is essentially X from an Algebra 1 class in middle school. It's not it's just an unset variable. It's just a name. I don't know. Kind of hard to define symbolic variables other than just a string. It's literally just a string that we associate with an unknown value. So we define our symbolic execution states as lists of relationships between these symbolic variables. So if I go back a slide, this is just a bunch of inequalities of symbolic variables, right? So our symbolic state is just a bunch of inequalities. Yeah, so the way that Angr actually does this is it uses another Python library called Clarify, and Clarify allows you to create symbolic variables. These are often referred to as ASTs. This is another term borrowed from compiler theory. There's reasons that it's called an AST, but we don't really care, so we're gonna skip it. Yeah, so Clarify allows us to create symbolic variables. We can add constraints to our symbolic variables and pass them into Angr. We can also evaluate these ASTs to find concrete values that match a constraint. So let's say we had, actually, I think I have an example 2 slides from now. So let's say we had like a system of equations and we wanted to find a specific input that matches this system of equations, right? We want to find like some like setting of all of the variables in our system of equations that makes it true. So the process of doing this is called sat solving. So it's satisfiability. So if we have some system of equations and we want to find a what's called satisfiable input for some like set of constraints, we do this by sat solving. So sat solving is an extremely hard problem. Like there's a lot of spooky math behind this. And I think if you're able to like solve arbitrary equations, it implies like P equals NP. So like yeah, if you were able to solve sat solving, then you just proved P equals NP. So this is very hard. Fortunately, there are open source sat solvers that do all of this for us, and we don't really care about the internals of this. We're just going to ignore it and say, oh, if we call this function, it sat solves for us. So here's the first like concrete code example of the talk. This is just using some symbolic variables. So we define x as a BVS with the name x of size 64. So a BVS is a bit vector that is signed. So this is essentially just a 64-bit signed integer variable, and we're naming it x. So then we can add the constraint that x is greater than 0x30 and x is less than 0x61. And then we can do the eval function, which finds some input that satisfies all the constraints on a variable. So in this case, I ran this beforehand and it gave me 56. So 56 is between 0x30 and 0x61. It's kind of a boring example, but you can imagine that if your inequalities were like crazy, then this is actually like super useful. So moving on from symbolic variables, we'll actually talk about the like Angr interfaces themselves. So the first one is the simulation manager. This is essentially the like main control interface to Angr. If you want to like do analysis, you do it through a simulation manager. So the simulation manager stores all of these simulation states, and it is what you call like if you wanted to do symbolic execution, you call functions on the simulation manager. So as an abstracted data structure, it might look something like this. We have a bunch of symbolic states. They have constraints, and they are currently executing like the basic block at 0x1234, for example. So our simulation manager just has a big list of these, and when we're doing the graph walk, we just like try to step each one of these states to the next basic block. So the simulation manager actually categorizes all of these simulation states, and it categorizes them into stashes. So each stash is just a list of states, and there's a few stashes. There's a lot of different stashes, but the ones we care about are active, dead-ended, errored, and unconstrained. So our new like abstract data structure of a simulation manager might look like this. So we have like a bunch of stashes in here, and each stash contains like some simulation state. Um, so like what are these stashes? So the active stash is the default stash for all states. So this is like states that are currently valid and that you want to do more analysis on. The dead-ended stash holds states that called exit or finished execution some other way. Um, so these are states that we probably don't care about anymore. The errored stash holds states that ended with an error, and the unconstrained stash holds states that uh, have a symbolic program counter. So the program counter has actually become a symbolic variable, and we no longer know where to go in the program to continue our symbolic execution. Um, so as far as like actually doing our execution, the simulation manager exposes a few functions that allow us to like perform the symbolic execution. So the first one is the step function, which just steps every active state one basic block forward. Um, so every state in the active stash is stepped once. There's a lot of S words in here, and it's kind of hard to say them. Uh, so yeah, so this is like the most basic symbolic execution task you can really do. There's two more that we really care about. One is the run function, which is just going to keep calling step until the active stash is empty. So this just like calls step until every path through the program has like exited, essentially. And then the explore function, which is probably the most important out of these, it calls step until some condition is satisfied by at least one state. So this is explore is really the one that we care about. If we go back to our example of like the reverse engineering problem, we could call explore and say like RIP is in some basic block would be our like end condition. So we would just keep running our analysis until we find that the program counter has moved into the good basic block. And then we would just sat solve based off of that. So before we can do anything with the simulation manager, the simulation manager takes as a like constructor argument a program state. So this is essentially the initial program state that the simulation manager is going to start analysis with. So using this initial state, we can directly constrain the registers in memory however we want, and then we can just start execution. So this gives us power over what possible paths we want the program to take. So there's a few like templated states that you can use. The blank state is just a state with no constraints. I don't really know any reason why you would use that, but I put it on here anyway. The entry state is a state with the program counter constrained to the start of main, and it also allows you to pass argc and argv, which is going to like constrain the value of RDI, the value of RSI, and the values of memory in order to properly set up like the execution state. Another one that's super useful is call state. So this is a state with RIP constrained to some other function. So instead of starting at main, we're going to start somewhere else, And like the entry state, it also allows us to pass arguments, and it's going to like automatically set the registers and memory to like properly set up the arguments. Each of these allows you to also pass a clarify AST as standard in. Remember that a clarify AST is just a symbolic variable. So we could create a symbolic variable that represents like a big string, and then we could pass that big string in as standard in. And that is probably what we'll do in most of our examples. So here's an example. This is going back to like the previous example, but instead of just evaluating x, I constrain RDI to be x. So say we were making some like, say we were creating some call state for Angr. We could say like, I don't know, maybe we're calling a Fibonacci function or something like that. And we could constrain the input to the Fibonacci function between 0x30 and 0x61 by doing this. Yeah. So in basic cases, we really just need an entry state with an unconstrained standard in. So this will essentially say, okay, there's some string that's being passed into standard in, and we are calling main. And then we call the explore function, which is just going to do the CFG walk until we find our like win address. And then we just use like a sat solver to on the unconstrained standard in, which should now be constrained to actually be the standard or the specific string that will get us to the win address. And then it's going to give us some input that we can put into the program, and it will take us to the win address when we use that input. Yeah, so that's like the basics of Angr. We're gonna talk about like a few more things, and then I'll do like a quick demo. So I said earlier that Angr has, or symbolic execution has like performance issues because of exponential state explosion. So the number of states that we need to keep track of is like roughly 2 to the n, where n is like the number of basic blocks we've processed. So if you think about it, this is going to prevent us from doing analysis on big programs, because we'll just like be running analysis forever. And I mean, I guess you could make the argument that eventually your analysis will finish in like 100 years, and then you'll like get the flag. But like, do we really care if we're going to get it in 100 years? Yeah, I mean, this exponential explosion problem is like a massive problem with symbolic execution. So there's a couple ways. Yeah. Kind of sucks, right? Damn, that blows. Uh, uh, we run into like huge problems, right? And this makes it important that we analyze as little code as possible. So we don't want to run symbolic execution on like setup functions. We don't want to run symbolic execution on like parts of main that don't do anything. We just want to run, we don't want to run symbolic execution on like error checking either. Like error checking, we don't care about that. So the call state template becomes very useful because in a lot of cases we only want to analyze one function. We don't care about the entirety of main. We don't care about like how main reads in strings and like how you interact with like the command line. We only care about finding the input to our function that like returns true, essentially. So another problem that we run into is with unconstrained loops. So if we have loops whose conditional variables are not constrained, they like slow down our model a ton. So we run into this problem because at any point we can either exit the loop or continue the loop. And what this is going to do is one state, it's going to generate one state continuing the loop. So one state is always going to stay inside the loop. And then at every step, it's going to generate another state that's leaving the loop. So essentially, we're generating one new state every step that's almost identical to the previous state. So if our loop condition is not well constrained, then we're going to continually generate more states and we're going to have bad performance. This commonly occurs when we pass like symbolic strings to programs. So using strings in C, we often have while loops that are conditioned on like null characters. So we're going to run like a while loop that is going to exit when we find the end of the string. So our loop can just, or our symbolic execution can just say, oh yeah, that string hasn't ended yet. And the state's like never going to leave the loop, which kind of sucks. Here's a picture of this, right? We're going to create two states, the green state and the red state, and at every state, or at every step, we're going to make a new green state, and at every step, we're going to make a new red state. So we're going to essentially generate a whole ton of extra states that we don't really care about. And so how do we fix this? The main point is that we need to make sure that loop variables are properly constrained. In most cases, this just means that we need to find like a max length that we want to pass for strings, and then constrain the final character at that max length to be 0. And that will prevent us from like going over. We'll see an example of this in the demo as well. And then the last thing for performance is like libc functions, right? So libc functions contain an absolutely massive amount of code that we don't want to analyze. Like there's so much error checking in libc that we don't care about. There's like so much like looping and random garbage that has like really no effect on our analysis. So this just causes a massive slowdown for us for no real reason. Yeah, that sucks, right? So by default, Angr actually doesn't even perform symbolic execution on libc functions. Instead, Angr creates what are called hooks for each libc function that gets called when you jump to a libc function during symbolic execution. So what happens is each hook is some Python code that just skips the analysis of the libc function and just directly constrains the program state like through Python code. So this requires Angr to have hook implementations for every libc function, but I guess we don't really care about that because Angr already did it for us. So here's an example of like what the Python hook for malloc might look like in pseudocode. So when we call malloc, we're just going to generate some address, bind the return value to be that address, and then mark that address as already being outputted by malloc. So this is like 3 lines of code. It's probably 1 line of Python code. And it's like infinitely faster than symbolically executing the like 2,000 lines that make up malloc. So this allows us to essentially get around libc functions without really doing anything. Unfortunately, some of the Angr hooks are buggy. So I submitted like a pull request a while ago to like fix some of them. I think most of them are fine. It's just like some of them don't work. I don't know. So we can also write custom hooks to skip the overhead of analyzing like arbitrary, uninteresting functions that are in our binary. So this isn't limited to like dynamically loaded libraries. Like say there's some function in your binary that like sets up memory to do something. We can just skip that function, right? We don't want to do analysis on that function. It sounds boring. Nobody really cares about it. So we just make like a hook that is empty. So it just does nothing. And it allows us to completely skip code, or we can make hooks that try to implement code in a fast way, similar to how Angr does libc. This hooking model is also used with like syscalls and like other dynamic libraries. Okay, last two things real quick and then the demo. So for exploit generation with Angr, we can also use Angr to like generate exploit payloads. It's not only a reverse engineering tool, it's also a binary exploitation tool. So for example, consider like a normal buffer overflow, but the data in the buffer overflow is encoded with some like wonky encoding scheme that we don't really know how to predict. So here's a picture of this. We're overflowing the buffer with some data that's computed by a function f. The like return addresses are also affected by whatever f is, and f is particularly hard to predict. So what we really want is for f sub n plus 2 of x to be some attacker controlled value, right, in order for us to take control of the program counter. But we've already said that f is like hard to predict, so getting f to be some user controlled value is difficult. So the way that we can actually do this using Angr is I talked about earlier that the simulation manager has a stash called Unconstrained, which means that the program counter is symbolic, right? So if we were to perform a buffer overflow in our symbolic execution, then the program counter is now going to be symbolic because we've overflowed it with like symbolic data. So let's say we find some unconstrained state. Then we can like sat solve for the input that sets RIP to a specific output. So we take our unconstrained state, we add the constraint that like f of n plus 1 of x is equal to whatever address we want, and then we sat solve. And this is either going to give us an input that will make f of n plus 1 of x be this address, or it's going to say, hey, there's no such input that does this. And then in that case, we could just pick a different input and try some other exploit. Or sorry, pick a different address and try some other exploit. And this same technique can be actually used to automate exploit generation, which is pretty wild. I don't know, might be a cool idea for a CTF problem. I don't know. Automatic exploits sounds crazy. And then finally, using Angr to find bugs. So static analysis as like a concept is generally not used when looking for bugs in your code. Instead, we use a different technique, which is called fuzzing. So the way that fuzzing works is we just generate random inputs and put it into the program and see what happens. And this might sound terribly inefficient, but because like the actual execution of fuzzing, like we're just running the code, like that's fast, right? And symbolic execution is like super slow. So because fuzzing just is so much faster, nobody really uses symbolic execution. The only downside is that when we're fuzzing, we're unlikely to hit bugs that have very few reproducing inputs. So let's say there's like 3 inputs that exist that are going to cause a specific bug to occur. There's probably like billions of other inputs that could be inputted instead. And I mean, like, what's the likelihood that you hit the 3 in a billion input that is going to trigger a specific bug? So static analysis is actually nice for this specific case. So if we have very uncommon bugs that wouldn't be picked up by fuzzing, we can actually pick them up using static analysis with our like symbolic execution. So this is actually called concolic execution, which is like a mixture of symbolic and concrete. And this gives us the power of static analysis and the speed of dynamic analysis. So what we do is we just fuzz normally, and if we find some path that's like never been taken, we can use Angr to find an input that hits that path. And then this just gives us better code coverage than is otherwise possible. Okay, that is the end of the slides. I'll do a quick demo. I don't know how quick the demo is going to be, but it'll be a demo for sure. Share screen. Make sure I share the right terminal. Okay. Can people see this?
Yes.
Okay.
Yeah.
So here's our like sample code. If we were doing the actual CTF challenge, we wouldn't have access to this, but it just reads a string, calls this encode function, and then does like a mem compare and prints nice flag or like get good. And this is actually the exact program that I like pulled the pictures from these slides off of. And our encode function is just like a XOR cipher of the flag. But I mean, let's just suppose that it's something like way more complicated than that, and we don't actually want to reverse it. So the way that we do this is we just like import Angr, import clarify, and then we like start using Angr. So the first thing that we have to do is like create a project. This just essentially loads the binary. So if we like look at the binary, we can see that it is pi enabled, which is going to change our exploit by like a few characters, because we now need main ops equals base adder 0. So this is essentially just going to say load the binary sample, and because it has pi, just assume that the like pi offset is 0. And we would just need to add the pi offset to every address that we're going to use. So then what we're going to do is define a symbolic variable for like the flag. So we can do that like this for I in range. We'll just limit the flag length to 32. So this creates a bit vector of size 8 that is signed. So this is just 32 chars essentially. And this is just like a Python array of 32 symbolic variables. So then we can do like password AST equals clarify dot concat, and then password chars. So this is just going to like concatenate all these symbolic variables into one big symbolic variable. And then we can go about like actually defining our state. So we can do like proj.factory.entry state, and then standard in equals password AST. So this is just defining the like starting initial state to be the entry state. And if you remember, this is the one that just starts execution at main, and we're able to pass in argc and argv. However, we don't need to do that here, so we're just not going to give it argc or argv. So then we can do define the simulation manager. So this is proj.factory.simulation manager. And then we just hand it the initial state. And then we can actually do our analysis. So we do simulation manager.explore, and we want to find and avoid some addresses. We don't know what those are yet. We can quickly go find out what they are. So if we do obj dump on the sample binary, so here is main. We see mem compare here. That's probably what we want to be looking at. Test EAX, jump not equal to 0x1259. So that is going to be the false case, is 1259. If we like look here, it's like loading something into RDI and calling like puts. So this is probably printing the get good string. And then if we didn't jump to 0x1259, we would have gone to 0x1243, which is loading some string and calling puts. So this is probably printing the nice flag string. So we want to find 0x1243 and avoid 0x1259 in our analysis. So find, I said 0x1243 and avoid 0x1259. And if we had picked a different base address here for pi, we would just need to add that base address to these numbers. I think by default, Angr uses like something stupid like 0x600,000 or something like that. Okay, and this is just going to run the symbolic execution, and then we can check the found stash, which is just like after we run explore, if it found anything, it puts it in the found stash. So we can say like print solution found, and then do found equals sim manager.found 0. So just take some arbitrary state that it found. This is a list, so we just like take the first one. And then we have the found password as found.solver.eval password ast cast to bytes. And this is going to compute the password, and then we can just do printf %s found password, else print, this should be print, no solution found. Cool, yeah. So if we do this, sample2.py, if I didn't screw it up, it should print the flag. Cool, it printed the flag. Okay, so that is the end of the talk, and now I will open it for questions.